This is problem 11.26 from your board problem sheet. We have a puck of mass 80 grams and radius 4 centimeters. I'm going to draw that in pink here. We have a radius of 4. And it's going to glides across an air table at a speed of 1.5 meters per second. And it is going to make a glancing collision with a second puck that has a bigger radius. Of 6 centimeters and a mass of 0.120 kilograms. I think this was supposed to be 0.8. It was 80 grams, so 0.08 kilograms. And when they collide, the rims are just going to touch. So this guy's going to come right over here and strike this guy right along the rim. And after the collision, the pucks stick together and rotate. And we want to find the angular momentum of the system relative to the center of mass and find the angular speed. So the first thing I'm going to do is set up a coordinate system where this lower puck here that's in blue is going to define my x-axis right through the center of that puck. And this guy is going to define my y-axis. So I'm first going to locate that center of mass. So the formula to calculate center of mass is YCM. We're going to take the mass of this blue puck, which is 0.120, times the distance that its center is from the origin. And because I put the origin right through that center, that distance is going to be 0. Plus the mass of the pink puck, which is 0.08, times the distance its center is from the x-axis. So to get to where they just collide, we have to go up to 6 centimeters of the blue disc, plus 4 centimeters more for the pink disc. So this guy would be at y equals 10, for example. And so those are the only two pucks making up that system. So we'll divide that by the total mass of the system, the 0.120 plus the 0.08. So if we complete that all out, the numerator divided by the denominator gives me a total of 0.04, which means that our center of mass is at the 4 centimeter mark. So since this guy is 6 centimeters, our center of mass basically runs right through here. Okay? So to figure out the momentum that this puck has relative to that center of mass, we use the formula I omega. As a point mass, that inertia would be mr squared times omega, which would be mr times r omega, which is mrv. And so I can get the angular momentum of this puck from about the center of mass by the mass of the puck, which is 0.08 kilograms, times r, which is the distance from the center of mass that this guy is moving. So our center of mass is at 4 centimeters. This guy's up here at 10. So the distance between the center of mass of the puck and the center of mass of the system is 6 centimeters. And that's what this r is here. Times the velocity, the linear velocity of the puck, which was at 1.50 meters per second. So the angular momentum of the pink puck before the collision is the product of all that. 0.08 times 0.06 times 1.50. Or 0.0072 kilogram meter per second. Now individually, these guys are spinning like they are a disk. So individually, the spin of this disk and the spin of this disk is related to the moment of inertia. I equals 1/2 mr squared for a disk. So for the pink guy, that moment of inertia will be 1/2 mr squared. That's the moment of inertia about its center. By the parallel axis theorem, if we want the moment of inertia about the center of mass, we have to shift that axis a total of 6 centimeters to its new location. So this guy is the radius of the puck, but md squared will be shifting due to the parallel axis theorem. So this is for the pink, and then for the blue we do the same thing. So I'm going to put little p's here for pink and b's here for blue. And then the total of a moment of inertia will be that sum. So we have 1/2 the mass of the pink puck, which is 0.08, times the radius of the pink puck, which is 0.04, squared, plus the mass of the pink puck, 0.08, times the distance that the axis is shifted off the center of the pink puck to the center of mass, which is a total of 0.06. And then for the blue puck, 1/2 times its mass times its radius, plus how much it's shifted off its axis. So we started here at the origin, the center of mass of the blue puck, and the center of mass of the system is 4 centimeters from that. So the parallel axis will shift 4 centimeters. 0.04 meters. So our total moment of inertia then, if we calculate all that out, is 0.0076 kilogram meter squared. So in the presence of no net torque, so there is no net torque here, the torque that this pink guy causes on the blue guy is equal but opposite to what the blue guy causes on the pink guy. So no net torque, angular momentum is conserved. So I'll do that part over here. If angular momentum is conserved, then the initial momentum has to equal the final momentum. And the final momentum will be the moment of inertia about the center of mass times the rate of angular rotation. So a different kind of formula, because in the first part we had a linear velocity rather than an omega, so we are calculating the angular momentum about that center of mass. So here our angular momentum to begin with was 0.0072. Our total moment of inertia was 0.0076, and we want to find omega. So 0072 divided by 0076, I think I've got off a 0 here. That should be 3 zeros. Sorry. Is 9.47. So down here when I calculated the moment of inertia, I recorded the wrong value. That's actually got an extra 0 in it, 0.00076. So this guy has an extra O up here. Okay. So again, we find the center of mass. We compute the angular momentum about that center of mass by the mass of this guy times the radius, which is the distance from the center of mass, times how fast it's moving. When these guys collide in a glancing collision, this pink one will start spinning to upward, so that would be, whatever that is, counterclockwise. So this blue guy is going to get pushed and start spinning clockwise. And the center of rotation, or the center of spin, will be at that 4 centimeter mark. So again, that was problem 1126. It was on your board problem sheet for chapter 11 problems.